Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 11th physics, get more than 95% marks, system of particles and rotational motion. Chapter 7, NCERT line by line, part 5. If you have not already subscribed our channel, please subscribe it and click on the bell icon so that you will not miss any of our important videos. Please like this video and share this video with your friends and relatives. Today we'll start with the topic 7.7 torque and angular momentum. So first we'll discuss about moment of force, that is also known as torque. We have learned that the motion of a rigid body in general is a combination of rotation and translation. So rotation and translation. If the body is fixed at a point or along a line, it has only rotational motion. We know that the force is needed to change the translational state of a body, that is, the to produce linear acceleration. So for linear acceleration, we need a force. We may then ask what is the analog of the force in the case of rotational motion. To look into the question in a concrete situation, let us take an example of opening and closing a door. A door is a rigid body which can rotate about its fixed vertical axis passing through the hinges. What makes the door rotate? It is clear that unless a force is applied to the door, it does not rotate. But any force does not do the job. A force applied to the hinge line cannot produce any rotation at all, whereas a force given magnitude applied at right angle to the door and its outer edge is the most effective in producing rotation. This is not the force alone, but how and where the force is applied is important in rotational motion. So main important thing, how and where the force is applied. The rotational analog of force is moment of force. It is also referred as torque. So moment of force and torque can represent the same thing. We shall first define the moment of force for a special case of a single particle. Later we shall extend the concept to system of particles including the rigid body. We shall we shall also relate it to the change in state of rotational motion, that is angular acceleration of a rigid body. Now, if a force acts on a single particle at a point P whose position with respect to origin O is L is equal to R P perpendicular, given by the position vector R, in figure 7.18. The moment of force acting on the particle with respect to origin is defined as the vector product tau is equal to r cross f. Now let us see the figure. So in this figure, this is x-axis, this is y-axis, and this is z-axis. We have a point here at P, and the length of this point is given as P perpendicular R, L is equal to R perpendicular P. Now F is acting in this direction, which makes an angle theta with the position vector R. The position vector R represents the point P's position from the origin O. This all explains the figure. And one more thing, if we have find out this value as by a trigonometric rule sine r sine theta, since this is r and it is related by sine theta is equal to perpendicular by hypotenuse. So sine theta, so sine theta into h, p is equal to sine theta, h into sine theta. So what is the value of p? H, what is the value of h? R sine theta. So perpendicular, so in this case the perpendicular is this line, this line. So this is the perpendicular and its value is r sine theta. In this way we have found out. Okay, because this angle is theta, so this angle is also theta, vertically opposite angle. Now let us see. So they it is said that torque is the cross product of position vector r and f, where r is the position vector of point P and f is the force exerted on r. The moment of force or torque is a vector quantity. The symbol tau stands for Greek letter tau. The magnitude of tau is equal to rf sine theta. So what is the magnitude of tau? Since the magnitude of uh, tau is equal to r cross f. So this is vector, this is vector, this is vector. So um, AB vector A cross B is equal to AB sine theta. So similarly, magnitude of R, magnitude of F sine theta and unit vector N. So RF, we can write it RF sine theta, the magnitude of RF sine theta. Tau is equal to the magnitude of, and direction is the unit vector direction N. So here tau is equal to RF sine theta, and this is equation 7.24a, where r is the magnitude of the position vector r and the length OP. F is the magnitude of f and theta is the angle between r and f as shown. Moment of force has dimension ml2t minus 2. Its dimension, so it is important for the objective questions. Its dimension are the same as that of work or energy. This is also important for objective questions. It is, however, very different physical quantity that works than work. It is different than that of work. Moment of force is a vector while work is a scalar. So remember, what is the difference between moment of force and work? Moment of force is a vector quantity and work is a scalar quantity. They can twist the question and can ask, okay, see, moment of force and work has the same dimension, that is ml2 t minus 2. So are they same physical quantity? No, they are not same physical quantity. Why? Because one of the big differences, work is a scalar quantity and moment of force is a vector quantity. That is the biggest difference. The SI unit of moment of force is Newton meter, and the magnitude of moment of force may be written as tau is equal to r sin theta f. R sin theta can be written as perpendicular distance of r and f, or tau can also be written as r f sin theta, that means r perpendicular force, where r perpendicular is equal to r sin theta, the perpendicular distance. Of the action of force F from the origin, and F perpendicular is equal to F sin theta is a component of force in the direction perpendicular to R. Note that tau is equal to 0 if R is equal to 0, F is equal to 0, theta is equal to 0. If all these values are 0, then tau is equal to, theta is equal to 0 or 180, then tau is equal to 0. Thus, moment of force vanishes if either of the magnitude of the force is 0 or if the line of action of the force passes through origin. Now, one may note that since R cross F is a vector product, properties of vector product of two vectors apply to it. If the direction of F is reversed, the direction of moment of force is reversed. If the direction of both R and F are reversed, the direction of moment of force remains the same. So this is important, that if we change the direction of R or F one at a time, then the moment of force direction will also change. If we change the direction of R and F both, there will be no change in direction of moment of force. So this is the vector property, cross product property of vectors, which can be implemented in this case also. Now 7.7.2, angular momentum of particle. Just as the moment of force is the rotational analog of force, the quantity angular momentum is the rotational analog of linear momentum. So what is angular momentum? Angular momentum is the rotational analog of linear momentum. We shall first define angular momentum for the special case of a single particle and look at its usefulness in the context of single particle motion. We shall then extend the definition of angular momentum of the system of particles including rigid bodies. Let moment of a force like moment of a force, angular momentum is also a vector product. So angular momentum is also a vector product. It could be referred to the moment of linear momentum. From this term, one could guess how angular momentum is defined. Consider a particle of mass m and linear momentum p. At a position r relative to origin O. The angular momentum L of the particle with respect to origin O is defined as L is equal to R cross P. The magnitude of angular momentum vector is L is equal to Rp sin theta, where P is the magnitude of P, that is linear momentum, and theta is the angle between R and P. Or we can write R perpendicular P, where R perpendicular is equal to R sin theta is the perpendicular distance of the directional line of P from origin, and P perpendicular is equal to P sin theta is the component of P in the direction perpendicular to R. We expect the angular momentum to be 0. L is equal to 0. When L will be equal to 0? If the linear momentum vanishes when P is equal to 0. If the particle is at origin. Again, if the particle has no distance, it is in the original distance. No distance from the origin, that is the particle is sitting on the origin, then also angular momentum will be 0. If the direction of the line of P passing through the origin theta is equal to 0 or 180, if theta is equal to 0 or 180. So in three cases the angular momentum will be 0. First case is if the linear momentum is 0. Second case is if the object is not moving, it is in the origin only, that is r is equal to 0. And if the angle theta is equal to 0 or 180 degree. In all the three cases, angular momentum will be equal to 0. The physical quantities moment of a force and angular momentum have an important relationship between them. It is the rotational analog of relation between force and linear momentum. For deriving the relation in the context of single particle, we differentiate L is equal to R cross P with respect to time. So upon differentiation, we get dl upon dt, differentiation of R cross P upon dt. Applying the product rule of differentiation to the right hand side, we get d r cross p upon dt is equal to dr upon dt multiplied by p plus r multiplied by dp by dt. Now the velocity of the particle is v is equal to dr by dt. and P is equal to mv. Because of this, dr by dt multiplied by P is equal to V multiplied by mv is equal to 0. As the vector product of two parallel vectors vanishes further, since dp by dt is equal to f. Therefore, we can write r dp by dt is equal to r, and dp by dt, rate of change of momentum, is known as force. So r cross f is equal to 2 tau. Hence d r cross p is equal to tau. Now we can write dl by dt, r cross p can be written as L dl by dt is equal to tau. Thus, the time rate of change of angular momentum of a particle is equal to torque acting on it. So this is very important. If we want to explain the equation 7.27 in words, then we can write the time rate of change of angular momentum of a particle is equal to the torque acting on it. This is the rotational analog of equation F is equal to dp by dt. So this is the rotational analog of the equation F is equal to dp by dt, which expresses Newton's second law of translational motion of a single particle. Now let us do further analysis. Torque and angular momentum of a system of particles. So we have done till here, we have done the torque and angular momentum of a particle of a particle. Now we are trying to find it out, torque and angular momentum of a system of particles. To get the total angular momentum of a system of particles about a given point, we need to add vectorially the angular momentum of individual particles. Thus, for a system of particles, we can write L is equal to L1 plus L2 plus dot 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 Ln, which is equal to sigma I is equal to 1 to n I L Li. The angular momentum of ith particle is given by Li is equal to Ri multiplied by Pi, where Ri is the position vector of ith particle with respect to the given origin, and P is equal to MIVI is the linear momentum of the particle. Next, the particle has mass mi and velocity vi. We may write the total angular momentum of the system of particle as L is equal to sigma Li Li. Again, it can be written as sigma I Ri cross Pi. This is the generalization of the definition of angular momentum of 7.25a. For a single particle of system of particles. Using equations 7.23 and 7.25b, we get dl by dt d sigma Li upon dt sigma I dl I upon dt, which is equal to sigma I tau I. Now where tau I is the torque acting on the ith particle. Tau I is equal to Ri Fi. tau I is equal to Ri cross Fi. The Fi on the ith particle is the vector sum of external forces acting on the particle, and the internal forces Fi ex, internal forces Fi internal exerted on it by the other particles of the system. We may therefore separate the contribution of external and internal forces to the total torque. So tau is equal to tau I sigma I tau I, which is equal to sigma I R I F I, as tau is equal to tau external plus tau internal, where tau external is equal to I sigma I Ri Fi external, and tau internal is equal to sigma I Ri Fi internal. We shall assume not only Newton's third law, that is, the force between the two particles of a system are equal and opposite, but also that these forces are directed along the line joining the two particles. In this case, the contribution of internal force to the total torque on the system is zero, since the torque resulting from each action-reaction pair forces is zero. We thus have tau internal is equal to 0, and therefore tau is equal to tau external. So the total torque is due to the external torque, since the internal torque value is 0. Since tau is equal to sigma tau I, it follows from the equation 7.28a that dl by dt is equal to tau external. Thus, the time rate of total angular momentum acting on the system taken about the same point. Equation 7.28b, the generalization of single particle case for of equation 7.23 to a system of particles. Note that when we have only one particle, there is no internal force or torques. Equation 7.28b is the rotational analog of dp by dt is equal to F external. Note that like equation 7.17, equation 7.28b holds good for any system of particles, whether it is rigid body or individual particles, having all kind of internal motion. Now, conservation of angular momentum. If tau x external is equal to 0, equation 7.28b reduced to dl by dt is equal to 0, or L is equal to constant. Thus, if the total external torque on a system of particles is 0, then the total angular momentum of the system is conserved, that is remains constant. So total angular momentum is conserved. The equivalent, therefore equation 7.29a is equivalent to three scalar quantities. Lx is equal to k1 dot ly. So Lx is equal to k1, Ly is equal to k2, and Lz is equal to k3. Equation 7.29b. Here k1, k2 and k3 are constants. Lx, Ly and Lz are the components of total angular momentum vector L along x, y and z axis respectively. The statement that the total angular momentum is conserved means each of the three components is conserved. Equation 7.29a is the rotational analog of equation 7.18a. That is the conservation of law of total linear momentum for a system of particles like equation 7.18a. It has application to many practical situations. We shall look at the few of the interesting application later on this chapter. So let us solve one example. 7.75 7.5, find the torque of the force. So this is the force given about the origin. The force acts on the particle whose position vector is this. So position vector and force are given. So R is given here, and step 1 we write the values which are known to us and given in the sum. R and F values are given. So tau is equal to cross product of F and R, and just by determined we have written ijk 1 minus 1 1 7 3 minus 5. Upon solving we get this one, and upon solving we get this one. So tau's value we know. Now the next sum, show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. So this is one of the important questions which can be asked to prove in your school exams. Let the particle with velocity v be at point P at some instant t. We want to calculate the angular momentum of the particle about arbitrary point O. The angular momentum, so we have drawn this angle is theta, this angle is theta, this is point P, this is moving this side with a velocity v, uh, and this is the position vector r, this that is OP's distance r, and so OM is equal to r sine theta. Now the angular momentum L is equal to L is equal to r into mv. Its magnitude is mv r sine theta, where theta is the angle between r and v as shown in the figure 7.19. Although the particle changes its position with time, the line of direction of v remains the same, hence OM is equal to r sine theta is a constant. Further, the direction L is perpendicular to the plane R and V. It is onto the page of the figure. So this direction does not change with time. Thus L remains the same magnitude and the direction is therefore conserved. And is there any external torque on the particle? So the basically we have proved here that L remains the same in magnitude and direction. Therefore, it is conserved. That is the main purpose here. So, next, again, for the people who have, for whom I have went very fast, then let me explain again this sum. So, let us consider a particle with a velocity v, at point P at some instance t. When we calculate the angular momentum of the particle about arbitrary point O, the angular momentum L is R into mv. Its magnitude is mv r sine theta. So important points are angular momentum is equal to r into mv. Again, its magnitude is mv r sine theta, where theta is the angle between r and v. Although the particle changes position with time, the line of direction of v remains the same. Hence, OM is equal to r sine theta is constant. Further, the direction of L is perpendicular to the plane of tau of R and V. It is onto the page of the figure. This direction does not change. Therefore, L remains the same in magnitude and direction. Therefore, linear momentum is conserved. Angular momentum is conserved. Therefore, angular momentum is conserved. So let us now do 7.8 equilibrium of rigid bodies. So in the first paragraph, it is said that we see the effect of linear momentum and torque in a rigid body, and thus the effect of angular momentum on a rigid body. So a rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changing with time. Are not changing with time. The body has neither acceleration nor angular acceleration. This means the total force, that is the vector sum of the force on the rigid body, is zero. That is F1 plus F2 plus dot 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 Fn is equal to sigma I is equal to 1 till n Fi is equal to 0. If the total force on the body is 0, then the total linear momentum of the body does not change with time. Equation 7.30 gives the condition for the translational equilibrium of a body. Second, the total torque, that is the vector sum of the torque on a rigid body, is 0. That is T1 plus T2 plus dot 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 Tn, which is equal to sigma I is equal to 1 till n tau I is equal to 0. If the total torque of a rigid body is 0, the total angular momentum of the body does not change with time. Equation 7.30b gives the condition for rotational equilibrium of the body. Equation 30a and equation 30b both are vector equations. They are equivalent in three scalar equations. Each equation 30a corresponds to sigma I is equal to 1 to n f Ix is equal to 0. Sigma I is equal to 1 till n f I y is equal to 0. Sigma I is equal to 1 till n sigma I z is equal to 0. This is equation 7.31a, where Fix, Fiy and Fiz respectively are respectively xyz components of the force Fi. Similarly, equation 7.30b is equivalent to the force Fi. Similarly, equation 7.30b is equivalent to the three scalar equations sigma I is equal to 1 to n tau Ix is equal to 0, sigma I is equal to 1 till n tau Iy is equal to 0, and sigma I is equal to 1 till n tau I z is equal to 0. This is equation 7.31b, where tau ix, tau iy, and tau iz are respectively xy and z components of torque Ti. Equation 7.31a and 7.31b gives six independent conditions to be satisfied for mechanical equilibrium of a rigid body. In, in a number of problems, all the force acting on the body are coplanar. Then we need only three conditions to satisfy the mechanical equilibrium. Two of these conditions corresponds to the translational equilibrium. The sum of the component of the force along any two perpendicular axes in the plane must be 0. The third condition corresponds to the rotational equilibrium. The sum of the components of the torque along any axis perpendicular to the plane of, of the force must be 0. So linear and angular momentum, in this way both should be 0 for equilibrium of a rigid body. A body may be in partial equilibrium, that is, it may be in translational equilibrium or not in rotational equilibrium, or it may be in rotational equilibrium or not in translational equilibrium. Consider a light that is of negligible mass rod AB at two ends A and B, which two parallel force both equal in magnitude and applied perpendicular to the rod as shown in. So this is rod AB. This is C is the midpoint, that is center of mass passing through C. Two parallel forces are acting on the two ends at A and B. Let C be the midpoint. ABCA is equal to midpoint of AB, that is CA is equal to CB is equal to A. The moment of force AB will both be equal in magnitude. AF. So moment of force will be F is tau is equal to A into F. But in opposite in sense as shown, they are opposite in direction. The net moment on the rod will be 0. The system will be in rotational equilibrium, but it will not be in translational equilibrium. So it in this case it is in rotational equilibrium but not in translational equilibrium. Sigma f is not equal to 0. The force at B in figure 7.20b is reversed in 7.21b. 20B. Thus, we have same rod with two equal and opposite forces applied perpendicular to the rod, one at the end A and other at end B. Here, the moment of both the forces are equal, but they are not opposite. They act on the same sense and cause anti-clockwise rotation of the rod. The total force on the body is zero, so the body is in translational equilibrium, but it is not in rotational equilibrium. Although the rod is not fixed in any way, it undergoes pure rotation, that is rotation without translation. A pair of equal and opposite force with the different lines of action are known as couple. A couple produce rotation without translation. When we open the lid of a bottle by turning it, our finger are applying a couple to the lid as shown in figure 7.21a. So this is one of the examples of couple. Another known example is compass needle. In the Earth's magnitude field as shown in the figure 7.21b. This one. So here also, this is also an example of a couple. Equal and opposite forces. Equal and opposite parallel forces are acting in a compass. So Earth's magnetic field exerts equal forces on the north and south pole. The force on the north pole is towards the north and the force on the south pole is towards the south, except when the needle point in the north-south direction, the two forces do not have the same line action. Thus, there is a couple acting on the needle due to the Earth's magnetic field. So, examples of couple and its implementation, examples like opening the lid, like compass, these are important scientific reason questions which we should expect in our exams, class exams. Let us solve one of the numerical example 7.7. Show that the moment of a couple does not depend on the point about which you take the moment. So consider a couple as shown in figure 7.22 acting on a rigid body. The force F and minus F acts respectively at point B and A. These points have position vector r1 and r2 with respect to origin. Let us take the moment of force about the origin. So this is the origin. R1 is the position vector and R2 is the position vector of A and B from the origin, and one force minus F is acting at A and plus F is acting at B. Let the moment of force about the origin, let us take the moment of force about the origin. The moment of force of the couple is equal to sum of the moment of the two forces making couple. So R1 into minus F plus R2 into F, that is R2 into F minus R1 into F, that is R2 minus R1 is equal to into F, but R1 plus AB is equal to R2, so we can write R1 plus AB is equal to R2. Therefore, we can write uh, AB is equal to R2 minus R1. Therefore, we can write AB into F, the moment of force couple. So we'll put the value of AB here. So AB into F. Clearly, this is independent of origin and the point about which we are looking moments of the force. So it proved that it is independent of from the point which we are looking. Principle of moments. We'll start this topic in our next class. So let us recapitulate what we have done today. Today we have started our lesson with moment of force, torque and angular momentum. First we have learned about moment of force, which is a combination of rotational and translation motion. After that we have studied that torque is nothing but it is a moment of force about a point. Tau is equal to position vector r and f. So it is a cross product of position vector and the perpendicular force. So either the force is perpendicular, we take the perpendicular component of the force along the position vector direction, or we take the perpendicular distance from the force. So both can be taken. So magnitude of tau is equal to r into f sine theta. Since it is a vector product, therefore it follows all the rules of vector product. Next we have studied about angular momentum of a particle. So here we have raised that raised derived so here we have derived a equation for angular momentum, that is angular momentum is a vector product or cross product of position vector r and linear momentum p. So L is equal to r, the magnitude of L is equal to r p sine theta. So since this is also a vector product, therefore it follows all the rules of vector product. Now we have proved that differentiation, if we differentiate or if we find the rate of change of angular momentum, we get tau, the torque. So torque is nothing, the rate of change of angular momentum, we can say. So torque and angular momentum for a system of particle, we have found that how torque can be implemented in equation of torque can be implemented in a system of particle. So we have found tau is equal to position vector r cross force. Again, the magnitude of tau is equal to r f sine theta, where theta is the angle between f and position vector force and position vector r. We have also found that the rate of change of momentum is the external force. We have done few sums related to the torque, and we have also done the equilibrium of a rigid body, where we have studied that rigid body is said to be in mechanical equilibrium if the linear momentum and angular momentum are not changing with time. Next we have learned about uh, about couples, what are couples, and what are the examples. So, uh, examples where couples are implemented. For example, compass and lead of a bottle, opening a lead of a bottle are the good examples which can be seen quite often. And in the next class, we'll start with principle of moments. Before we close, please subscribe our channel if you have not done yet. Please like this video and share this among your friends and relatives. Thank you all for your support and watching our videos, and wish you a very good luck for your class exams, board exams, and IIT, JEE, NEET, and other examinations. Thank you very much.